Hello everyone, can you hear me? Okay, so we have discussed what is the formula for the first principal component analysis, how we derive it. We have seen what a principal component means. We saw that principal components are the rotated versions of the original coordinate axis. Today we are going to see a few more mathematical properties of principal components, okay? And um, how those are helpful in achieving what we want to achieve. Okay, so one thing we have seen last time is that first PC is actually an eigenvector corresponding to the first, the largest eigenvalue, right? This is what we have seen. First principal component is actually a linear combination. And how does that come into picture? So let me try to write. Wow. Oh, okay. Wait. Okay, so first PC is L prime X. You can see my screen, right? Where you can see my screen, right?
Yes, ma'am.
Okay. Where L is a p-dimensional vector such that L is a normed eigenvector corresponding to the largest eigenvalue. Normed eigenvector corresponding to the largest eigenvalue of sigma matrix, that is variance covariance matrix of X. Up to this point we have seen, right? And I had asked you to derive equation for second PC. Some people have already tried that and the derivation is almost the same, so there is a very less chance of making any mistake. So second PC turns out to be, so maybe I can write this as L1 prime X, largest eigenvalue we denote by lambda 1. Then second PC turns out to be L2 prime X, where L2 is an eigenvector corresponding to lambda 2, that is the second largest eigenvalue, correct? So we had already seen that lambda 1 is largest, lambda 2 and so on, lambda p, and all of them are non-zero. Actually all of them are positive. Is it okay? So second PC turns out to be this, and in general I can have pth PC as LP prime X, where LP is an eigenvector corresponding to lambda p. Okay. Now we have also seen that variance of L1 prime X, or if I want to write in general terms, variance of any Lj prime X will be Lj prime sigma X Lj, This is just formula for variance of linear combination which we have studied in the preliminary lectures. Okay. And because Lj is an eigenvector corresponding to lambda j, I would write this as Lj prime sigma L will become lambda L. So that is lambda j Lj. Everyone okay with this substitution? Sigma L would become lambda L by your eigenvalue eigenvector relation Ax equal to lambda x. Okay so far?
Yes.
Then lambda j is a scalar, so I can take it outside. So this becomes Lj prime Lj. But we are already putting a constraint that this is a normed eigenvector. So this becomes simply lambda j. So variance of the jth principal component is actually the jth largest eigenvalue of the sigma matrix. Okay. And what about covariance? So if I compute covariance between say PCI and PCJ, then this becomes covariance of Li prime x, Lj prime x. Okay. So this we know from the formula that we studied in preliminary lectures, that is this would be Li prime sigma x Lj, which would become Li prime sigma x Lj. I will again write as lambda j Lj. So this is lambda, even if you can't see it, this is supposed to be lambda. Okay, so this is, again I will take lambda outside because it's scalar, so it becomes lambda j Li prime Lj, and we know that these eigenvectors are chosen in such a way that they are orthogonal to each other. That was one of our constraints in the what we call Lagrange's multipliers. So lambda I prime lambda j is actually 0, and hence my entire answer is 0. So covariance of ith PC with jth PC is 0 as long as I is not equal to j. Okay, which means that the PCs are orthogonal to each other. Okay, PCs are orthogonal to each other, and that actually implies they are uncorrelated with each other. We just now proved that their correlation is 0, and uncorrelatedness or orthogonal nature indicates that the information that each one of them providing is completely free from the other. Means we don't have any redundancy. Whatever first PC is telling me, second PC is telling something additional. Okay, second PC is not repeating even a part of what first PC was telling me. Okay, we saw this problem in the earlier, in the usual coordinate setup. If my two variables are correlated, highly correlated, then knowing one does give me some information about the other. So the information given by the second variable is not completely new. Part of it is already obtained from the first variable. Whereas when I am saying that the principal components are orthogonal to each other, this would mean that the information provided by each one of them is completely new. Okay, they are not dependent on each other. They don't share any information content. Okay so far? Okay, so if x1, x2, xp denotes the original vector, and y, which is y1, y2, yp prime, denotes the corresponding PCs, then we know that yj is Lj prime x, that much we know. Then now we have to find, is there any relationship between sigma x and sigma y. Okay, what is sigma y? Sigma x is going to be something unknown. What is sigma y? Just now we have derived that variance of jth PC is lambda j. So sigma y would be lambda 1, lambda 2, lambda p, and we also proved that covariances are 0. So this would be 0, 0, 0. So basically sigma y would be a diagonal matrix whose diagonal entries are eigenvalues of sigma x arranged in the decreasing order of their magnitude. Is it okay? This is the variance covariance
Yes, ma'am.
matrix of the principal components. Okay. Now, when we want to compare, see, in univariate setup, variance is a single number. So, comparing variances or saying that one variable is having higher variance than other is easy. However, in the multivariate setup, we know that for a vector, we have an entire variance covariance matrix. So, comparing two matrices is a bit difficult exercise. So, people have proposed some measures by which we can represent an entire variance covariance matrix with the help of a single number. So, two important of them are known as total variance and generalized variance. Okay, total variance and generalized variance. So what is total variance? Total variance is basically okay, fine, let me ask you a question. Given any matrix, I want you to in some way represent that matrix by a single number. So what are your options?
Determinant.
Determinant, correct. Determinant is one option. Anything else?
Trace.
Trace. So these are the exactly two things that we are going to use. So total variance is basically trace of sigma matrix and generalized variance is determinant of sigma matrix. Okay. So what is interesting about PCA is PCA preserves the total variance as well as the generalized variance of the original vector. Let me repeat. PCA preserves the total variance as well as the generalized variance of the original vector. What do I mean by preserve? What I mean is trace of sigma x, that is total variance in the original vector, is same as trace of sigma y, that is total variance in the PCs. Okay, and similarly determinant of sigma x is same as determinant of sigma y. Okay, of course we have to prove this. How do I prove this? Now trace of sigma x, what all things do you know about trace? What is trace basically? What is definition of trace?
Sum of the eigenvalues.
Sum of the
Eigenvalue.
eigenvalues. Okay. Uh, what about easier definition? Sum of eigenvalues is correct, no doubt.
Sum of the
Any
diagonal entries.
sum of the diagonal entries, correct. So we are going to use both these definitions. So trace of sigma x, we will use the definition that we got first. So trace of sigma x is sum of eigenvalues of sigma x. Okay, and what are eigenvalues of sigma x? We know they are lambda 1, lambda 2 up to lambda p. Okay, so this is sum over lambda i's, I going from 1 to p. And now I'll use the second definition. I can see that for sigma y, lambda 1, lambda 2, lambda p are the diagonal entries. Okay, So sum of lambda I is nothing but sum of diagonal elements of sigma y, which is nothing but another definition of trace of sigma y. So this is same as trace of sigma y. Okay. So we have proved that total variance of the original random vector is same as total variance of the PCAs. Principal components. Okay so far? Now the generalized variance. So what do I know about determinant? What do I know about determinant?
Product of eigenvalues.
Product of eigenvalues, okay. So let me use that definition first. So determinant of sigma x by that definition will be lambda 1 into lambda 2 up to lambda p. Okay, so this will be product over I going from 1 to p lambda I, and we can see here sigma y is a diagonal matrix. And what do I know about determinant of a diagonal matrix? Do I know something about determinant of a diagonal matrix?
Product of diagonal entries.
Product of diagonal entries, correct. So this would be determinant of sigma y. Okay. So generalized variance of the original vector is same as generalized variance of the principal components. So the total as well as generalized variance both are preserved when we construct principal components from a given random vector. Everyone with me so far? Is there anyone who did not get this? Okay, so from silence, I would assume that everyone is following whatever is happening here. Now we are going to use this concept of total variance for dimension reduction. Now you must have thought this that initially I focused and I said that PCA is needed for dimension reduction, but so far we have P original random variables and we have P PCs. So we have not achieved any dimension reduction as such. Okay, so that we will do now. Okay, so how do I use principal components for dimension reduction? So instead of using all the P PCs y1, y2, yp, I will choose to use only a few. Now, two questions. How many and which? Okay. How many yi's and which yi's? The question of which yi's is in most cases solved very easily because we know that the principal components are arranged as per their variation. Correct? Ordered as per the variation, and we know variation is information. So they are ordered as per their information content. Okay. PCs are ordered as per their information content. Okay. So the first PC has the highest amount of information, second PC has the second highest amount of information, and so on. So once I fix the number, once I fix the dimension which I want to achieve, for example, let's say I decide that okay, my P is 100, but I want only 5-dimensional data, then the question of which is automatically solved. Because the first PC has most information, for us it is most important. Second PC is second most important, and so on. So if I fix somehow that I want 5 PCs, I will go for first 5 PCs, that is for sure. Okay, first 5 is fixed. I don't need to worry about that. Now, how many pieces should I go for? 5 or 10 or 20 or 90? That we have to decide. For that, we are going to use this total variance thing. Okay. So, suppose I want to go from say 100 variables to some less number of variables. When I say I go to less number of variables, of course I have to lose some information. I cannot retain entire information with less number of variables. Some information of course I have to lose. So we have to decide how much is how much part can I afford to lose. Okay. So can I lose say 10% information, or can I lose say 20% information and still have not much of an issue, and so on. Okay. So we compute what is called as proportion of variation explained by individual pieces. Okay. Proportion of variation explained by individual principal components. So how do I compute this? We saw the concept of total variance or total variation. So total variation is sum of lambda i's. Okay. And we know that jth PC, for jth PC variance is lambda j. Therefore, proportion of variation explained by jth PC is lambda j upon total variance. Okay. Explained by jth PC is lambda j upon sum over lambda I going from 1 to p. Okay, proportion of variation explained by jth PC is lambda j upon the total variation. And of course, if you want percentage, you can multiply this number by 100. And now, because first PC is most important, it will explain the highest proportion of variation. Second PC will explain second highest proportion of variation, and so on. Okay. So, cumulative proportion of variation, explained by say first k PCs, would be sum over j going from 1 to k lambda j divided by sum over I going from 1 to p lambda I. Okay. So we have proportion of variation explained by those first k PCs divided by total variation. Okay. And this quantity is generally used in deciding how many PCs one should retain for further analysis. So if suppose I have 10 variables, that is my P is 10, and say out of these 10 variables, two variables are explaining two PCs are explaining 75% variation, and if I'm in a domain where it is okay to lose 25% information, then I will say just consider 2 PCs instead of all 10 PCs. Okay, just consider 2 PCs instead of all 10 PCs, because those 2 PCs are giving you 75% of whatever information you had with all 10 variables. So less efforts and still decent amount of information. Is it okay? How you decide how many PCs one should retain for further use? Yes or no? Is it okay?
Yes, ma'am.
There is another method for deciding this, because the problem is this is an objective method, no doubt about that. But the thing is, sometimes I may not have enough domain knowledge to decide how much loss of information can I afford. Can I afford 10%, 20%, 30%? I don't know. I may not have enough domain knowledge to decide that. So to handle such situation, there is another method for deciding how many PCs should be retained in further analysis, and that is known as scree plot. Okay. So what is a scree plot? It's a very simple graph. As the name suggests, it's a graph. It's a very simple graph. On x-axis we just have indices 1, 2, 3, 4 up to p. Okay. And on y-axis we have the eigenvalues. So the first eigenvalue is supposed to be largest, hence suppose it is here, then second is suppose here, third is here, fourth is here, and so on. Okay, and we join these eigenvalues by a straight line. Okay, somewhere here I have points. And we locate what is known as elbow. Okay, so this is an elbow for the obvious reasons, right? You can see why it would be called as an elbow. So if this is an elbow, what it means, something is an elbow means the graph is almost parallel to x-axis after that point. Okay, what is the meaning of an elbow? The graph is almost parallel to x-axis after that point, and before that there is considerably steep slope. Okay, and before that there is a considerably steep slope. Then what it means is all the remaining PCs, for all the remaining PCs including this one of course, means third, fourth and so on, the importance or the contribution by these PCs in variation is more or less similar. Okay, it's parallel to x-axis means it's more or less similar. Remember, this is not going to be exactly parallel. It's almost parallel. Okay. However, the earlier PCs contribute much more. So if elbow is at kth position, then we take k minus 1 as the important number. Okay. So we take k minus 1 as the number of PCs that should be retained in further analysis. Is it okay so far? This plot is known as scree plot, and if you don't have domain knowledge, then you use elbow in a scree plot to decide the number of PCs that should be retained in further analysis. If elbow is at kth position, then you say that kth point onwards, kth PC onwards, everything is equally contributing and hence equally insignificant. So you take first k minus 1 PCs. Okay. So this is scree plot to decide number of PCs. There is another plot which is associated with PCA. It is known as score plot. Actually, it is needed in applications also. Today we will just see the plot, how the plot is constructed. So what is score plot? So we have to first compute what are known as PC scores. So what do I mean by PC scores? So we say that Lj prime x is the equation for jth PC. Okay. Now instead of this x, if I put entries corresponding to ith observation here, then I get a particular value, a single value, and that would be score of ith observation on jth PC. Let me repeat. So suppose I have L11x1 plus L12x2 plus L1pxp as first PC. Okay. Then suppose I have an observation 1 whose values are something, Then if I substitute these actual values of observation 1, you see where observation 1 is, right? It's a row it's a row from your data matrix. So if we substitute those values here, and L11, L12 up to L1P are of course known because they are eigenvectors, then we get a single value which would be known as score of first observation on first PC. Okay, score of first observation on first PC. In general, for every PC and for every observation, we can compute this. So for every observation PC combination, so we have what is known as a score matrix. Okay. What is the order of score matrix? Score matrix is of the same order as the original data, that is n cross p, where ijth entry is score of ith observation on jth PC. Okay, ith observation on jth PC. How do you compute these scores? You compute these scores by using the eigenvectors. Okay, now I have some homework for you. So homework is try to work out what would be the matrix formula in terms of matrix for computing scores. Okay, and once I have the score matrix, we use the first two columns of that score matrix. So this becomes O1, O2, On, scores for observation 1, observation 2, observation n, and it is PC1, PC2 up to PCP. Okay, so we plot the first two PCs on a bivariate graph, and that is actually known as score plot. Okay, the graph of first two PCs is known as score plot, and the score plot has a lot of applications, especially in classification. Okay, let me stop here. In the next lecture we'll continue with the applications. Thank you.